here.
Can we have that one slow?
Yeah, we'll do another one, but later.
Slow motion.
All right, in the solution we have copper 2 ions and sulfate ions. And then the zinc bar, we just have zinc atoms. In the solid state, just some crystalline zinc here, like this. And so what happens is this. Copper 2 is an oxidizer. Oxidizers want electrons. Yeah. Sulfate's also an oxidizer, but sulfate you need to have some H plus present in acid solutions. So sulfate can be a decent oxidizer in acidic conditions. But under these two, you know, we have these two competing oxidizers. Copper 2 is going to be the better oxidizer. Now zinc, metals are a good source of electrons, right? And typical metals take these on. And so what's going to happen is the copper 2 is going to, you know, collide with the surface of the zinc, and in those collisions we can have transfer of electrons occur. And so what will result is that the copper 2 plucks an electron to form copper solid on the surface, and the zinc is going to come off the surface to form a Zn2+. Let's do it this way. So we got a redox reaction. In other words, copper 2 is oxidizing the zinc solid to form zinc 2+ plus copper solid. And so as far as the driving force goes, we're going from a stronger oxidizer to a weaker oxidizer and a stronger reducer to a weaker reducer here. And so this reaction occurs spontaneously. We can break this reaction up into two half reactions though. And so if we look at the net reaction is going to consist of a reduction half reaction and an oxidation half reaction. And so the reduction half reaction is copper 2 plucks 2 electrons to form copper solid. And the oxidation half reaction is that zinc gets oxidized to form Zn2+ plus 2 electrons. In this reaction, the electrons are transferred directly, you know, from the copper to from the zinc to the copper, sorry. And so we have direct transfer of electrons. And so what we want to do here in building a battery is we don't want the electrons to go straight from the zinc to the copper. What we want to do is we want to route the electrons from the zinc through a wire to the copper. And so how are we going to do that? Well, the way we're going to do that is we're not going to do it in a one beaker reaction like that. What we're going to do is we're going to put the zinc in one beaker and the copper in another beaker. And what we want to do is we want to attach these two with a wire. And so to attach these with a wire, we're going to take our multimeter and pull one of the wires off the multimeter, either wire. And then we have a clip here. You should have two alligator. Do you have two alligator clips? You have two alligator clips? Mine only has one. Pull one of the alligator clips and put an alligator clip on both sides, and we're going to make a jumper wire. And so there should be an alligator clip on one side and an alligator clip on the other. There's banana plugs on here. And so you're going to pull an alligator clip off one of these wires and then attach it to the other end. And so we have a jumper wire with two alligator clips. do we have enough alligator clips to do that? How many alligator clips do you guys have? Two. That's all you need. That's all you need because we're only making one wire.
Oh, we did do one wire?
Yeah, only one wire.
So we're gonna have to put those in.
Okay, so this is what we're going to do here. Oh, let me diagram it up on the board. Okay, basically what we want to do is this. You know, over here we have the copper 2 ions. The sulfate's a spectator, so I'm not going to show those. And then over here we have a stick of zinc, solid. And what we want to do is we want to attach one alligator clip to the zinc here. And then we're going to route the wire, the copper wire, actually, over to this solution here. Okay, but if you take a look, do you see the banana plug on the end of the wire? The banana plug is galvanized steel, I think. You know what galvanized steel is? It's tin-coated steel. And so if you were to dip the banana plug in here, we're dipping tin into it. Is copper 2 a strong enough oxidizer to oxidize tin metal? Yes. And so we don't want to dip the banana plug in here because the copper 2 will take the electrons straight from the zinc, not the zinc. Yeah, actually it is zinc, right? The zinc-coated steel. And so what we need to do is we need to get some way to feed the electrons that are going to come from zinc to copper 2. And that some way is we need something that conducts electricity but won't react with the copper 2 ions in there. And so what conducts electricity but won't react with the copper 2? Copper metal. If we use copper metal, then copper 2 and copper metal, that just yields the same thing. So there's no reaction, no net reaction. So we don't have to worry about it. But we don't have to use copper metal. Is there an alternative we could use? Yeah, back there is an alternative, and that alternative is called graphite. Lead metal would react. You know, graphite won't react. Graphite, carbon's very hard to oxidize. Graphite conducts electricity, and so if we use graphite, that is just elemental carbon, put a stick of graphite in here, do the same thing. And so this thing that's feeding the electrons to the copper 2 is called an electrode. Electrode is just this conduit for the electrons. And so what we need here is we need an inert electrode. And so I'm going to attach, you know, the alligator clips are kind of reactive because it's just galvanized steel. And so what we're going to use is an inert electrode. This is one of the reasons why we had so much platinum and gold in our lab, because oftentimes we use those as electrodes, inert electrodes, because platinum and gold are very unreactive. And so inert electrodes, the usual ones are gold, platinum, graphite. Graphite's cheap. And in this case, copper would be an inert electrode. Sometimes copper is not an inert electrode. You know, and so let me put a little asterisk there. Because if this were more powerful oxidizer than copper 2, it would attack the electrode. We don't want it to attack the electrode, right? We just want it to supply electrons. And so what we're going to do is we're going to use copper metal. And so what does copper 2 want? Copper 2 wants electrons. It's a good oxidizer. And so copper 2 tries to take the electrons off copper metal. It's going to have a tug of war. Copper versus copper, who's going to win? It's going to be a tie, right? And so nobody's going to Nobody's going to win. But electrodes, you know, these conduct electrons, and so electrodes, you know, have freely conducting electrons. So that means there's a sea of electrons here. And so copper 2 is trying to pull the electrons off this electrode, but it's not going to be successful. And then attached to this electrode will be our steel alligator clip. And that conducts electricity, so we're going to have a chain of electrons. And then this wire is made out of copper. And so we have this long chain of electrons that eventually ends at zinc. Over here. So when copper 2 is pulling on an electron over here, do you know who's feeling it? Zinc is feeling it. Does that make sense? Because the electrons are being pulled, which is pulling this electron, and all these electrons are going to be pulled along the chain. And therefore, what we can do is this. Let's try this. We're going to take our copper metal and put it into the copper 2 solution. Like this. And then we're going to clip our wire to the copper metal. And then in the other beaker, we're going to have our strip of zinc. And we'll attach the other end of the wire to the strip of zinc. Yeah, it's just sitting in air. So just leave it in air. Did you guys do that? Don't put it in any solution. Just leave it dry in air. Huh? No, leave it. Leave it.
It already reacted.
Not already reacted? All right, you can dump it in the waste. All right, make sure goggles, you guys. We want everybody safe here. All right, this is being attached to the zinc. The zinc is just sitting in an empty beaker. Is that what you have? Now let me ask you this. Is copper 2 a strong enough oxidizer to strip electrons off zinc? Is copper 2 a strong enough oxidizer to oxidize zinc? Metal. Yes, right? And so what's going to happen is here, there's going to be a zinc atom here, and the zinc atom is going to lose 2 electrons to form Zn2+. Correct? And so what we should do is we should start having a flow of electrons because we got a lot of zinc here. We got a lot of copper 2 here. As the copper 2 pulls these 2 electrons off here, it's going to start depositing copper metal on copper. And so do you see copper metal being deposited on the copper? It forms tiny crystals of copper. Tiny crystals of copper look black. Do you see a black coating forming? No. No, so somebody tell me what's wrong with this. I mean, that's all we needed. Did you mix any zinc solution with your copper when you dipped your zinc metal in the copper solution? That's all we started with, right? We started with a bar of zinc and copper 2. And we dipped the bar of zinc in the copper 2 and we got electrons transferred. And so we should see the same observation here. We should see deposits of copper metal. Do you see it? No. Why not? Why do we need solution on the zinc side? Okay, that's right. The reason is because now the zinc 2 plus is in air, right?
Okay.
And so what we need is we need solution on the zinc side. What solution do we need? Well, we need like water. Would water work? Yeah, water should work. And so why don't you pour some water? DI water. This is important because of this. Is Zn2 plus stable in air? No. But is Zn2 plus stable in water? We form Zn2 plus aqueous, much more stable in water than it is in air. And so by forming Zn2 plus aqueous, that'll help stabilize the products. Right, because when we're looking at chemical reactivity, we also have to look at not only how reactive the reactants are, but how stable the products are. And so this goes back to acid strength. When you're looking at acid strength, not only do you look at the reactivity of the acid itself, but you also have to look at the stability of the conjugate base that forms. And so we gotta think about what types of things help stabilize the conjugate base. One thing is hydration, like this. Okay, so did you put water in there? Do you see some crystals of copper metal depositing on the copper? No. No. Why not? Do you know why not? Can somebody tell me why nothing's happening now?
Water's not.
There's something very important happening because now what are we forming as a product? We're forming Zn2 plus AQ. If you want a pure Zn2 plus AQ solution with nothing else in it, is it possible? It's impossible. Why? Yeah, there's no anion. And so this is just a solution of cations. If you wanted to go buy a bottle of just cations, I don't want any anions, I just want cations. Is that possible? Impossible. Why? Because if you think about the accumulated positive charge here, you're going to generate a voltage so huge as to be incredibly unstable. You know what this is called? It's called a space charge. We're all familiar with space charges because we get electrical shock. You know, if you build up too much charge on your body, you're going to ground out, right, on something. Well, the same thing here. We can only build a minute quantity of Zn2 plus before the space charge gets too high and the voltage gets too high. It becomes terribly unstable. And so it stops. And so I need to eliminate the space charge here. But not only do we get a space charge here, we also get a space charge here because we're losing cations. As we're losing cations, do we lose anions too? No, the anions stay fixed. And so what's happening is this beaker is becoming increasingly negative. This beaker is becoming increasingly positive. And we get the separation of charge. When we get a separation of charge, that's called a voltage, and the voltage is going to stop this from happening. And so we have to eliminate the space charge. How can we eliminate the space charge? Well, one way is if we introduce anions over here. and we introduce cations over here. But we want an anion and a cation that are inert. We don't want anions and cations that are going to react. And so how can I sprinkle in anions here and cations here? Is there a way I can just sprinkle those in to eliminate the space charge? I don't sprinkle them in, but I'm going to let them diffuse in. The way I'm going to let them diffuse in is I'm going to use potassium ions for the cation. So over here, I'm going to feed in potassium ions. The potassium ions are going to neutralize the negative charge of the sulfates, right? As we're consuming the copper 2s. And then over here, I'm going to put in chloride ions. Well, zinc and chloride don't react, so that should be no problem there. But how can I put the chlorides in over here and the potassiums over here? Well, it turns out it's very easy. And the way we do that is with a salt bridge. A salt bridge is, we're just going to get a piece of paper. We're going to get a piece of paper and then a petri dish, and then soak it in potassium chloride. Like this. So I have a piece of paper that's been saturated in potassium chloride. And then I stick one end of the paper in this beaker and the other end in that beaker. And so now there's potassium chloride in electrical contact. And so what can happen is the chlorides migrate over here, the potassiums will migrate over here, maintaining electrical neutrality in my salt bridge. And so the last step here is I need to add a salt bridge like this. And this is going to be KClAq. And so the chlorides migrate here. I'll need 2 chlorides for every Zn2+ that forms. And over here, the potassiums migrate. And so for every 2 potassiums over here, I get 2 chlorides over here, so we maintain electrical neutrality. All right, now what you're going to do is you're going to do this. We're going to do 2 things. One, we're going to, because sometimes it's hard. Maybe the crystals are growing so slow you just can't tell, right? And so instead of using our visual detection of reaction, we're going to use our multimeter. And this multimeter on the voltage setting, we'll turn it to DCV 2000M. On DCV 2000M, the max is 2000 millivolts. And what that does is this. When we want to measure if electrons are flowing, what we do is we block off the line. We block off the line and feel, are the electrons trying to push from left to right here? If the electrons are moving left to right or being pulled left to right, then we should feel a pressure. And that pressure is called the voltage. And so the way a voltmeter works is it blocks the current. It's like capping a hose. If you want to measure the water pressure, you need to seal off the hose with your hand and then feel the pressure on it, right? If any leaks out, then you're not measuring the full voltage or the full pressure. Well, the same thing here. This is going to completely block the electron flow and just determine what the pressure, or what we call the electrical force or the electromotive force, EMF, is on this. In other words, the voltage. And so the voltage is the pressure on the electrons flowing through this. And so what we're going to do is we're going to reattach the lines here and then connect one of these to the copper and the other one to the zinc and see, are the electrons trying to flow from the zinc to the copper? Okay, we're going to do that before we put the salt bridge in there. And so first measure the voltage right now to see what the voltage is. Do you need a multimeter?
No, we didn't have
The clip? All right, how many volts are you getting? 0 volts. There's 0 volts because of the space charge, right? All right, now leave the voltmeter on there and make yourself a salt bridge, and then dip one end of the salt bridge into one beaker, the other end into the other beaker, and watch the voltmeter. The salt bridge is on the back bench there, or maybe it's up here. I have the potassium chloride up here. You just need a strip of paper.
Can I just dip it in?
Yeah, just go ahead and dip it. Yeah. Without the salt bridge? Oh, you have it on 2000N?
Yeah, that's the salt.
It's not supposed to be jumping around. Omar, use this multimeter. Is that in water? It's not supposed to be jumping around.
I made it too long. So it goes 0.
Make sure the contact between the alligator clip and your electrode is good. One of the electrodes is an earth, the copper. The other electrode is a reactive electrode. The other electrode is zinc here. All right, so everybody sees 0. Now add the salt bridge and see what happens to the voltage. If it's negative, flip the polarity. That is, swap the red and the black. If you come out with a negative voltage, the electrons are just trying to flow backwards to the meter, which just means just switch it. Put the red one on the other one and the black one on the other one. On the metal, not on the meter.
98.
No, not on the meter. On the metal.
Yeah, flip it on the middle.
On the electrodes.
Put it back
Leave it the same on the meter. The red one should go on the top, the black one in the middle. All right, are you guys getting a voltage? What is your voltage? 0.94 volts? 1.26 volts? 0.926? You're millivolts, so it should be, 900 something, right? Or 800. 900 millivolts. So everybody's getting about 900 millivolts? All right, the voltage is going to vary depending on, we have what's called, if there's any kind of resistance between the alligator clip and the electrode or whatever else, we'll get voltage drops. So don't worry about it too much. All right, now with the salt bridge, this is what we have. We're going to have electrons flowing from the zinc to the copper. Correct? And so electrons flow from the zinc to the copper. Normally we want the electron flow to be left to right. And so position the zinc on the left and the copper on the right. And so now we have the electrons flowing left to right here. And over here, what's causing the electrons to flow? What's causing the electrons to flow? Well, nothing. The electrons aren't flowing now. The electrons aren't flowing. Why aren't the electrons flowing now? Because the meter is preventing it. And so what you're going to do is you're going to pluck off the 2 alligator clips, then pluck off 1 alligator clip and make a jumper wire. With the jumper wire, connect the 2 electrodes directly. With a jumper wire, then there should be nothing blocking the flow of electrons, right? Uh-huh.
We're not getting any reading.
Do you have a solver?
Yeah. And I'm getting a reading here.
Okay, then let it sit. All right, make a jumper wire, and then we're going to let it sit and react.
Oh,
So now we're waiting.
Yes.
We're just getting -1.
Or unclip and then swap.
Swap.
Yeah. If you're getting a negative voltage, that means the voltmeter is just hooked up backwards. And so just unclip it and swap it.
That's where I think our multimeter has an issue. It's just staying that way.
Oh, okay.
Do you know where that we're like a little confused. Like, what's the point of unclipping and then swapping them?
I'll be there.
Are you gonna, yeah, are you gonna, is that cute? Like, you know how they ask you, like, a keeper something?
The purpose of swapping them is if you're getting a negative voltage. A negative voltage is the reason you get a negative voltage is because the voltmeter has a meter here, And if the electrons are being pushed this way, you get a positive voltage, right? But if you hook it up backwards, that is, if you hook it up and flipped around this way, then you end up getting a negative voltage because it's pushing the dial the opposite direction. That's all. And so that's why you swap it. But does everybody have the jumper wire back on there? All right. With the jumper wire, there's nothing preventing the electrons from flowing. So now the electrons are flowing from left to right here. The electrons won't flow unless there's a salt bridge. And so the salt bridge is going to just be this KCl solution in which the chlorides are moving this way and the potassiums are moving this way. This is KClH2. This is what we call our salt bridge. This is our external circuit. We can't build a battery with an external circuit alone because we have to maintain electrical neutrality. If all the electrons flow from left to right, then this is going to build up in negative charge, this is going to build up in positive charge. And so we have to have an internal circuit that reverses that. The internal circuit is different. In the external circuit, we have the flow of electrons. You know, electrons are our charge carrier. In the internal circuit, we have ions.
That'll be the salt bridge.
Or electrolytes. Yeah, this is the salt bridge, the internal circuit. And so in the internal circuit, we don't have any flow of electrons, we just have the flow of the ions there. Okay, the electrons get fed to the electrode here. Now, this was an inert electrode. We don't have to... It's an inert electrode because the electrode's job on the right is just to feed the electrons to our oxidizer. And what is our oxidizer? Copper 2. And so basically the reaction here, the copper 2 is taking the electrons to form copper metal. So I was asking you before, what is pulling the electrons through our external circuit? The copper 2. And so what's driving except resisting that is zinc. You know, zinc is going to have some kind of ionization energy. It might not be so easy to oxidize it. And so zinc is providing a little bit of resistance, but copper is overpowering it and pulling the electrons through the external circuit. Now, the electrodes have a name based on the ion that flows to them. And so in the internal circuit, potassium ions are flowing to this electrode. And so we call this the cathode. The cathode is because cations from the internal circuit go to this electrode. Over here, this electrode, which is a reactive electrode, because this electrode is made out of zinc. And so this electrode, just say reactive in parentheses here, is called the anode. It's the anode because the anions from the salt bridge are migrating to it. At the anode, we have oxidation because the copper 2 is oxidizing the zinc and pulling the electrons to form Zn2+, Aq plus 2 electrons. And the net reaction here is this. The copper 2 oxidizes the zinc solid to produce Zn2+ plus copper solid. We get net 2 moles of electrons flow for every mole of copper and zinc that react in this. Okay, and we generated voltage around 1 volt. Okay, are there any questions with this? No?
Why two fluorides, one here and one copper?
Oh, sorry. It's got to be 2. 2 chlorides and 2 potassiums. 2 electrons. Okay. Other questions? So this is the way we can make the electrons go through a wire in this redox reaction. We generate what's called an electrochemical cell. In an electrochemical cell, we have 2 beakers, one for the cathode, one for the anode. At the anode, oxidation occurs. You know, oxidation generates the electrons. At the cathode, reduction occurs. Reduction is consuming the electrons. And we do those separately. All right, what would happen? Dump out the water. Dump out the water in the zinc beaker and fill it with zinc sulfate. Okay, dump out the water out of the zinc beaker and fill it. Did you see any reaction? Sorry. No? Okay, it's slow. That's the reason why. Reaction's slow, so it probably takes more time. We'll try to speed things up here. All right, dump out the water and fill it with zinc sulfate solution. And then now remeasure the voltage. But before you remeasure the voltage, I want to ask you, what impact will that have on the voltage? Do you expect the voltage to go up, go down, or stay the same? If we dump in zinc sulfate rather than water, will the voltage go up, down, or stay the same? Go up? Go down? Or stay the same? Okay, why do you think the voltage will go up? You have 1 in 3 chance here. You guessed. But that's the wrong answer. It does not go up. It goes down. The voltage should go down. The voltage should go down. Measure it and see. Did the voltage drop? The voltage could have dropped for 2 reasons. One reason is the cell is operating. As the cell operates, some of the reactants get consumed, driving force decreases. So I should have done this earlier. But for sure, we expect the voltage to go down. Why do we expect the voltage to go down? Take a look at the net reaction and tell me why we expect the voltage to go down. One, you could call on Le Chatelier's principle. Sure. What does Le Chatelier's principle say?
We increase it at one sense and shift to
As you increase the concentration of the products, we expect a shift to the reactants. And so, what was the purpose of adding zinc? Does that make any sense to add zinc sulfate to the zinc? It makes no sense because, all we're doing is we're making a
saturated.
even worse battery. Does that make sense? And so we don't want to add any zinc sulfate here. We want to add water here. Right? Because the more zinc sulfate we put in here, the more product we have, the more this should shift to left. So it makes no sense to add zinc. Right? But why are we adding zinc? Why we're adding zinc is because when we do these voltages, we have reference tables for them. And the reference tables are based on non-standard conditions or standard conditions? Standard conditions. And so if we're doing things under standard conditions, what are the concentrations supposed to be? 1 molar copper and 1 molar zinc. It's ridiculous to put 1 molar zinc in there, isn't it? This is just going to decrease the voltage and push the reaction back. It's ridiculous. The only reason you do it is so that you can do it under standard conditions, so you could generate a voltage that's the same as the voltage that you get in tables that are generated under standard conditions. Does that make sense? But we wouldn't do this in practice, right? And so what we're going to do is this. We're going to take a look at how much time. You guys need a break. I have a video I want to show. Okay, so hold on just a sec. Or take a break. Let's take a break for 5 minutes. Or we'll start the video at noon.